Hello everyone, today we will be going over the blind 75 in C++, and today we are working with the problem word search number 2. Now, before we get started, in order to break down the following problem, and if you're also following along at home or wherever, we need to ask ourselves these 4 questions in order to break down the following problem. We first need to ask ourselves what the input's going to be, what data structure / algorithm / technique to use, what to do with the data, and finally what our output's going to be. So, breaking down the problem, given an m times n board of characters and a list of strings called words, we already know what our input is. Return all the words on the board. Alright. Each word must be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally or vertically neighboring. The same letter may not be used more than once in a word. So if we have a following input of characters that we have, we need to find adjacent characters coming together where there will be a staggering connection for the following. And so what we will do for the following technique is that I'll also put links for the following videos as well in the card section. Just press the eye icon on the top right corner. The technique that we're going to be doing to be able to replicate this following behavior is going to be a try data structure with depth first search. Now, why do we do this? Well, given the fact that one, we are dealing with a board of characters, which is a list of where we have a board of characters, and then we also have the words oath, pee, eat, and rain, for example. We're just trying to find these words inside of the list of the characters which are adjacent to each other. So we are trying to find the words with the given board of characters to find which words are in the board where the characters are adjacent to each other. And so the steps for us to be able to accomplish this for the following task are going to be the following. Step 1, we will initialize a try data structure and insert all the words into it. With each character. Step 2, we will create a list to store the found words from our character board. Step 3, we will loop over each cell in the board using depth first search for both the row and the column. Step 4, we will return the list of found words. So, just going over all the steps that we need to do. I'm also going to further expand this at the same time. So, step 1, what we will do ultimately is that to initialize a try data structure, we will need to do the following. Create a separate structure to initialize the try node, children, and word. So if I'm going step 1, step 2, step 3, step 4, step 1 is going to look like the following. We're going to move this out here so that we can call upon a public struct that we have, where it's going to represent try node, and then we're going to have a vector or try nodes for children. and then we're going to have a string called word. Then we're going to have a try node structure with children ranging from the English letters in the alphabet with a null pointer, and then word. This is just how we initialize our following. Don't forget the comments as well. And this is just how we set up everything with a try node structure. Now, what we will do for step 2 is that we will initialize the root of the try node, and then we will scan every word in the words list we are given. Scan every string in the words list we are given. That's a better way of putting it. And we will scan every character we visit in the word list. Then create a new node for each character in our try node structure to add what we have visited and we will move to the child node representing the current character. And finally, we will store the word at the final try node. And the way it's going to look like for step 2, we're going to do the following. A, B, C, D, E, F. Step 2 is going to look like this. Try node, root, new try node, then B, for string and word for words. We're gonna reinstantiate try node for node. Root, and we will scan the characters. Create a new character for So the way we are going to do D is that we're going to set up, assuming that we have not visited children, for C, A. I'm going to set that equal to the null pointer. So, node, children, for character, each one, We'll go to new try node to add to the structure, calling upon it, yes. Then we have E, where we're going to move the child node represent the current character. The way we do this is node equal node children C A, and store the word at the at the final try node for F. So node word. Then heading over to step 3. Is that we will create a list to store the found words. B, we're going to loop over each cell in the board, row and column, and inside we will perform def first search, and I'll also highlight how we will create our def first search function for later, but for the meantime we're just going to loop everything that we've already visited. So we will have a vector of strings, which will be our result, to store everything that we have visited. So for int I is equal to 0, I is less than the board size, and I is incremented. And it's for the row, and it's for the column. Int j is equal to 0. J is less than the board at the following index, and then size to indicate for this. Rows and columns, yes. Double check. And while doing so, we're going to perform def first search for a board I, j, root, and result. And this will be our function that we're going to create right over here. Def first search function. Yep, that's what we do. A, B, C. All right. To A, I'm just going to specify 2, 2, 2, 2, 2, 3, 3B, and then 3C. There we go. That's more like it. Just helping out with everything else. And then we will return a list of words, so it's going to be return result, which is our list we created over here. Now for the def first search function. Now the way it's going to look, I'm actually going to put this over here so we can go step by step accordingly for how this whole thing will be built. Is that for our def first search function, we're going to check if the current cell is visited or the corresponding try node for the current character does not exist. If so, if we have visited or is the corresponding try node we will just return nothing, and we're going to move along to the next node and then check if the current try node contains a word. If it does, we add the word to the list of found words and clear the word from the try node. And then we mark the let me just put this right here. 1, 2, 3, 3A, and then we're going to mark the current cell as visited, and then we will recursively perform depth first search, where there's going to be an element of recursion with recursion of the neighboring cells in directions up, down, left, right. So this is how we're going to build our depth first search function. It's going to be a private void depth first search with the following parameters that we created up here. So it's going to be vector for characters, and board, much like in the case over the parameters we have right here. Interestingly enough. Then we will have I, which will be int I, and then int j, and then try node with a vector, string, and result. There we go. Just double checking, because we're going to take the rows and the columns while scanning through and showing at the root to ultimately get a result. Much like in the case of taking the parameters that are right here, except for we have result that we will be returning instead of the words. So while scanning through them, we have step 1, step 2, step 3, step 4, and step 5. So step 1, what we'll do is that we first need to initialize our character at the given index. So we need board I and j. Just need to specify that. First initialize the current character at board, row, and column. Then okay, and then for 1A, right, if the current character has been visited, we're going to mark it like this with the pound, indicating that it is visited, or the node children for C and A indicate nothing's there. We're just going to put in return to indicate, hey, we don't have anything there. Then for the next step, we're going to move along to the next node. The way we do that is that we're going to do node is equal to node children C root A, and then what we will do, check if the current tree contains a word. We do so by the following: if the node, if the node for the word is not empty, indicated by the exclamation mark over there, then what we will do is that for our list that we have result, which is in a public structure that we're able to call. So we have result pushback for our node to word, and then we have node word right there. Step 4, we're going to indicate if the board has been visited, so we do so with I, j is equal to the pound. Then we're going to indicate for our directions up, left, down, or right. So this will be for the following. If I is greater than 0, depth first search board I minus 1 j. Then we have the node and the result. Oh, also, quick correction. So this would be for all of the directions that we have. Pause here. Okay, so this is how we do the directions. Just want to be sure on that. So up, down, left, and right. So I is going to be the key indication for every single row that we have, and J represents the column, so yes. So for down, if I is less than the board dot size minus 1, we're going to do a recursive call with the board I plus 1, and just move up accordingly J, node, and result. Make sure that we always have our semicolons. And then we'll do the same thing, except for it's going to be the left and the right, and we're going to deal with J. So J is at the very left, and then it should be J minus 1. And then for the right, if J is less than the board size minus 1, yes. So we have J plus 1. Yep, node, result. Alright. Dealing with I, yes. Dealing with J, just being sure if we have everything all correct. Okay, so this should be the result that we have. I'm just going to put these notes up here to showcase to you folks what we need. And just put this right here. There we go. Alright, avoid all of that. Here we go. That's more like it. Right there. And I'm going to keep all the notes together and then also showcase to you folks anything else. So this is where our depth first search solution, just trying to get it in frame. If I can do that. Okay, there we go. Let's double check on everything. Alright, so we have a syntax error. Make sure you keep your semicolons. And we have a runtime error. Yay. Okay, also for the right, given the fact that we are dealing with J, we have to be right here, over there. That makes sense. I forgot the 0 index to start with because board, since I represents rows, J represents columns accordingly, this should work. Nope. I also forgot to make this J. Alright, And there is one specific part that also needs to be added. That's the very last step for this. Part 6 is that we need to revert the current cell to its original state, indicating we have not visited. So, it should be looking like this. Board I of J is then equal to C, indicating that we have reverted the cell back to its current state. So let's try this again. Alright, it passes all the test cases. Let's submit this. Alright. Okay, we have the whole solution already set up in place. Now, to give a breakdown on the space and time complexity for our following solution, is that our time complexity for the following is going to be O of M plus N, where O of M is the total number of characters on the words, while N is the total number of cells in the board. And meanwhile, the space complexity for our following solution is going to be O of M plus L, where O of M refers to the total characters in all the words, and then L represents the stack for what we use based on the size of the given board and the length of the word, respectively, to each. So yes, this was Word Search 2. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put in the comment section. And as always, take care. Cheers. Bye-bye.